So what is case 2 here in this situation? Well, the case 2, remember the case 1 was when I had these 2 points P and Q that have the x-coordinates not being equal to each other. So case 2 would be when the x-coordinates of these 2 points are actually equal to each other. And I mean, what could that mean? Well, first of all, that could mean that the points P and Q actually lie exactly on top of each other, right? So there are different points on the curve that have the same x-coordinate. But that's not the case I'm interested in here. I'm actually interested in the case when P and Q are exactly the same point. And now, what could that mean? I mean, it looks kind of stupid to ask about something like that. So that means I somehow would like to draw a line that only intersects the curve at one point and ask in how many more points it can intersect the curve. Because, I mean, that just means having just one point rather than two. But now that we talked about these multiplicities, I can actually make sense of that question. Namely, what I mean here is that I have these 2 points, P and Q. I have sort of like 2 points, P and Q, except they're the same point. And then I'll think about that as a point of multiplicity 2. More precisely, as that the x-coordinate of that point gives you a root of this polynomial here that has multiplicity 2. So there will be a tangent line. So that the line L would be actually tangent to the curve. Multiplicity 2 or higher. Okay? So that's actually what I want to assume here. So let's maybe not write that, because this really doesn't really mean very much. So instead, we're going to assume, so suppose xp is a root of f of multiplicity bigger than 1. So what does that mean? So it's either multiplicity 2, so we have case A, xp is multiplicity 2, has multiplicity 2. xp has multiplicity 2. In that case, we already know what happens, so the line is tangent. Then L is tangent to E at P and doesn't cross it, right? Doesn't cross it at P. So it behaves like this point P prime here. It stays on the same side, right? So I'm just sort of draw this situation here, right? So we have this is the curve E, and this is the point P, and so here is the tangent line. So what do we know by our proposition? We know that there's going to be another point where this line intersects the curve. So by our proposition, we know there is a point R different from P where L intersects E. So the third and the most extreme case is when xp, well, part B of case 2, when the root is multiplicity 3. So we know what happens then. That means that, so i.e. f of x is equal to just x minus xp cubed. Okay, and I will not do the calculation here, but you probably already suspect. So first of all, the line intersects then the curve and only at one point, only at P, right? Then P is the unique point of intersection. Of L and E. And the line is actually tangent to the curve at that point, but it crosses it. and L is tangent to E at P, but crosses it. P is an inflection point. Okay, could I find an inflection point on this picture there? Kind of, right? I think I can. I think this looks like an inflection point. P double prime, inflection point. If I draw now a tangent line, you see it is actually tangent to this curve, but it crosses that P. And it never intersects the orange curve again. So let's just now maybe summarize this to have, after all this discussion, a clear picture of what can happen when we take a curve like this, a cubic curve, in particular this elliptic curve here, and a line. So we take this curve here, and one situation that can happen is, here's P, here's Q, and so the line I'm going to draw is not going to be tangent. As you see, it's not tangent. The line that connects these 2 points is not tangent. So it goes like this. Because it's not tangent to any of them, it must intersect the curve at yet another point. So here's the third point of intersection. The second case that can happen, so same curve, it's kind of bigger this time. If I take a point, let's say here P, and I draw a tangent line that stays on one side of the curve. This one stays completely above, right? So then I know there's going to be one more point of intersection. There has to be. Our proposition says so. No matter where you take this P, well, unless you take it here so that the tangent line is vertical. Okay, let me leave this case at the end. But no matter where else you take it, as long as you keep the line on the same side, you are going to find another point of intersection. So some sort of like, let's see, I take this point and that point, P prime, Q prime. I connect those two with a line. And it looks like maybe, oh, there is no other point of intersection. It looks like there isn't, but there actually is, because this line is here. The concavity of the line will force, the concavity of the curve will force the line to intersect again. So somewhere there is another point of intersection. It's same here, like if I take the point here, I don't know, like here, P prime, right? It looks like, oh, there is no other point where they're going to intersect. But the same thing is going to happen. This line eventually is going to meet that curve somewhere else down there. That's our proposition, right? Because this point now is a point where the line is tangent to it, so it's a root of multiplicity 2 to the equation given by y squared of E minus y squared L. So there'll be a third real root, so a third point of intersection. And then there was the third case where we take an inflection point and we draw a tangent line to an inflection point. So last time we took the inflection point above, let's now take it here. There's another inflection point here, right? And then I have this tangent line going like this. This is the point P. And you see this line is not going to intersect the curve anymore. It's sort of, we can think about it as it intersects the curve at P 3 times. Okay, that's one way to think about multiplicity. This line intersects the curve at 3 points, P, Q, and R. They're all distinct points. It intersects the curve at each of these points only once. Here we have this line intersects the curve at only 2 points. However, if I count multiplicity, this one has multiplicity 2. So I can say oh, it's a tangent, at P it's a tangent line that stays on the same side of the curve as it goes through P. So P is a double point. It intersects the curve at P twice. It's kind of like we cannot really see this physically, but that's an algebraic interpretation of it, because that would be a root of multiplicity 2. So it intersects the curve twice here and third time here. Counting multiplicities again 3 times. Same here, okay? In this last one here, it intersects the curve. The line intersects the curve only at one point. However, it intersects it at the point of multiplicity 3. So if you count multiplicity, it's still 3 times. No matter how you draw it, it is 3 times. Okay, so what's the case, the exceptional case that I have been so far avoiding? It's when these 2 points are on top of each other. Here, P, Q. Ah, my line just missed the point. All right, PQ. Okay, that clearly does not conform to these standards we have just been discussing. It is not tangent at P, and the line isn't tangent at Q. So these are all points of multiplicity 1. They are just single points, and it clearly will not intersect the curve anymore. Similarly here, you see if I take this point here, that's, I'm going to draw a line that is tangent at this point, vertical line, vertical. This point counts as a double point because the line is tangent to the curve and it stays on the same side, so it's a double point, but it does not intersect the curve anymore. So these are exceptional cases, and we're going to be talking about them when we talk about arithmetic of elliptic curves.